Hello, my name is Kendall Lamb, and this is Lab 5, Falling Slinky. The purpose of this lab was to model a falling slinky to see if the bottom of the model stays stationary as in the experiment. Below is a quick preview of the main result. The bottom was indeed stationary. There is also a quick look at the resulting graph. For physics concepts, first is Newton's second law, which says net force is change in momentum over change in time. We use this in the lab to model the motion of our slinky. The velocity update and position update equations were also used in GlowScript to model the motion iteratively. For forces in this lab, first is gravity, which has magnitude mg and is in the negative j hat direction near Earth's surface. Next is the force of drag, which represents air resistance. It is equal to a proportionality constant times the speed squared in the direction opposite of motion. Finally is the force from the slinky. In this lab, the tension force from the slinky pulls up the bottom to be stationary. When the top is dropped, the tension force is still there and the bottom stays still. The two different parts of the slinky drop are shown to the right. In phase 1, the force of tension counteracts the force of gravity, so the bottom is stationary. In phase 2, both the top and bottom of the slinky meet and it falls. For initial conditions, the mass is 0.2 kilograms, which was a guess based on the average slinky. The initial position was taken from tracker and the velocity is 0 since the slinky was initially in static equilibrium. Our system was the bottom of the slinky and the surroundings were the air, earth, and top of the slinky. Here we can see the tracker analysis. The bottom of the slinky is tracked in red and the position versus time data is plotted on the right. Looking at this graph, we can see that the position of the bottom of the slinky is remaining stationary until the top reaches it. This is because although the top has been let go of, the bottom is still being pulled up by the tension force. Now we are here in GlowScript taking a look at the code. First, we just set the initial conditions, mass, position, and velocity. This value b is a proportionality constant, which was found through trial and error until the position values ended at the same place. Now here's our first while loop, which represents the time when the top of the slinky is falling. We add the force of gravity and tension from the slinky for net force. Then we use velocity and position update formulas to update the motion. Then we plot everything. And now here's our next while loop, which runs afterwards. Now we have our net force equal to the sum of the forces of gravity and drag. Then we use velocity and position update equations to update the motion once again. And here we plot everything again. Now let's run the program. We can see it looks quite similar to the tracker graph. Now for the comparison. We can see that the two lines, orange for tracker and blue for GlowScript, look relatively similar but aren't the exact same. These discrepancies could be due to the possibility that some tension from the slinky could have remained even after the bottom and top met. There are also other sources of error that could have caused this. For example, some sources of error are camera's perspective, the slinky is not an ideal point mass, the drag model could have been inaccurate, and there also could have been other forces during the drop, such as wind. Now for the conclusion. Let's go back to the question. Is the bottom of the slinky in the model stationary? We can see based on the graph generated by GlowScript that it is stationary, at least during the phase where the top is still falling. Another interesting to note from this experiment is that the center of mass of the slinky falls at the rate of gravitational acceleration despite the bottom being stationary. Thank you for listening.